which I lifted right from the paper of Renew and well, so it hasn't always been clear that physicists love us using complex. So even though everything we do is based on complex filters, which makes all the theory tidy because we can diagonalize whenever we want to and things like that. It was never quite clear if not more is inherently complex. If we are forced to use complex numbers. And, there's this lovely paper that came out that shows that quantum theory based on real numbers can be experimentally falsified. They developed a Bell-like experiment based on a network scenario, which numerically detects if the underlying state spaces are real or complex. And trials have shown that the state spaces really are complex. And so why am I talking about real? Well, the reason I'm talking about real is reading this paper made me realize I didn't know or understand the differences really well at all between the real and the complex cases of separability. And I wanted to just chart exactly what the differences are, maybe help understand some of these differences. And so we took a look at all these concepts: entanglement, which we've seen, separability, positive maps, p-positive maps, things like that, and entanglement breaking maps, and this famous PPT squared conjecture of Andreas and Christendahl, and what the similarities and differences are in the real and complex case. In the real case, lots of authors like to look at the domain as being the real symmetric matrices, because after all, if you take the positives and take their linear span, you only get symmetric matrices. You don't get all real matrices. But it's if you want to use the Choi-Jamilakowska representation, then you really need the domain to be all of the matrices. And the other reason is if you are just acting on the symmetric matrices, it's not clear how you would extend to the real matrices. There's no canonical extension because the usual way of taking a matrix and projecting onto its symmetric part, well, that's to the map that sends x to 1/2 x plus x transpose, and that's not a completely positive map. So there's no canonical way to extend positive things on symmetric to positive things on all the real matrices. So it's just better to start with a linear map defined on the full matrix space. And so here's the first thing we want to look at. It's the notions of separable and entangled again. So when I want to be free with whether I'm talking about the real or the complex case, I'll use K. And so the separable maps, of course, are just the things you can write as sums and tensors of positive semi-definite matrices. And any matrix that's positive semi-definite, but not in that, is what we mean by an entangled matrix. The first question that's natural to ask is, if you have a real matrix and it's separable as a complex matrix, is it also separable as a real matrix? And in other words, if you take the separable complex matrices intersected with the real matrices, is that equal to the separable real matrices? And I'll call that set the C-sep. And since I gave it a different name, you probably are guessing already that means they're different. Yeah, so you can have matrices which are complex separable, but are not real matrices, which are complex separable, but are not separable as real matrices. And let's see why that's true. Why it's distinct. If we look at the canonical, I think this is the Y matrix, and you do I2 tensor I2 plus A tensor A. You get this 4x4 block matrix, which has all real entries. But you can also write it this way. So in the complex domain, that's a separable matrix. but it's not separable as a real matrix. You cannot write it as a sum of positives. And very way to see that is if you do have something that you can write as a sum of positive tensor positives over the real field, well, a positive matrix, a positive real matrix is equal to its own transpose. So if you apply the partial transpose map, it would fix separables. That's something that's very different in the real domain. The partial transpose fixes things which are separable, fixes them individually, doesn't just fix the set. And so since this matrix X is not fixed under partial transpose, it's not R separable, but it is complex separable. So, and then more generally, we'll talk about things that we call P-separable. Separable you can think of as if you take elementary tensors, X tensor Y's, and look at the corresponding rank 1 operators, it's the convex combinations of those. The P-separable are the things which are convex combinations of ranked 1s, which are Schmidt rank P. So, you have a U, which can be written as a sum of P rank 1s. And then, of course, we'll have C-seps of P, which are the things which are P-separable as complex matrices and happen to be real matrices. So the first theorem that we looked at is Sturmer's theorem and its generalizations, and see how that works out. And it's the same theorem. You have a linear map between your matrix spaces, real or complex, which is transpose preserving or star preserving, if you like. Then it's P positive if and only if, when you look at the Choi matrix paired with X's from the P separable, it's positive. So the P positive maps, their dual is the P separable matrices. And I think you all know that in the case when P is 1, because that's your entanglement witness idea. If something is entangled, if it's entangled, then there'll be a positive map that witnesses the fact that it's entangled. And so there'll be something where you can have the trace less than 0. So since it's the separables that are the dual to the P positive, well, what is this C separable all about? That's kind of natural to ask what that is, and that has to do with complexifications. If you have, anytime you have a complex matrix, you can write it uniquely as a sum of 2 real matrices, A plus IB, and anytime you have a linear map on real matrices, you can make it a linear map on the complex matrices just by this simplest way in the world. Just do phi tilde of A plus IB is phi of A plus I phi of B. And the theorem is that it's if you take a real map, then its complexification is P positive, if and only if, when you pair it with things from C sep P, you get positive values. So it's the cone of the things that have complexifications that are P positive, real maps with P positive complexifications. So that means we've got these witnesses that if you've got something in C sep that's not separable as a real matrix, so a real matrix that's separable as a complex, then that's witnessed by a phi tilde, which is P positive, and has, which that's negative. I'm sorry, by a phi, which is P positive, but its complexification is no longer P positive. So those are the witnesses that separate the C sep from the sep, things, the real matrices that are separable as complex, but not separable as real. Okay. So once you have these notions, the next natural thing to do is look at the theory of entanglement breaking maps, because after all, that has to do with separability of the Choi matrix of the map. So just to recall, if you have a CP map, it's called entanglement P breaking. If for every n, you take something which is positive in MN tensor MD, and when you apply identity tensor phi to it, it becomes separable. So that's the usual notion of entanglement breaking. It's that just pardon?
The parameter P level.
And the set P.
So you have a P which is in MN tensor MD positive, and you do id sub n tensor phi to that P. I like to think of them as block matrices.
I think we're talking about the small p, not the capital.
It comes in the set.
Oh, that's from the we have when P is 1, that's our usual notion of separable. These higher P's are when you start with rank vectors of Schmidt rank P and take their rank 1s and take its convex combinations. So with P equals 1, that's our usual notion of separability. Then there are these higher notions of separability. That's these seps of P sets. And they're natural because they're just the way that the separable is the dual of the positive maps. The seps of P are the duals of the P positive maps. And so P entanglement breaking is when you're not just separable, but you're separable, but of some rank, some P rank. And so when P equals 1, this is the classic Horodecki-Schor-Ruskai theorem. And then in between, it's been generalized to these higher P's. And the theorem's the same, whether just like with Sturmer's theorem, the theorem's the same whether you're looking at real or complex. So this is something else that stays exactly the same. So being P entanglement breaking is the same as the Choi matrix being P separable. And it's the same as you have a Choi-Krauss representation where all the Choi-Krauss operators have rank at most P. So P equals 1, that's saying they're all rank 1. And that's the same as when you pre or post compose with P positive maps, you become completely positive. So the P equals 1 case, you compose with positive maps, you become completely positive. That's the characterization of entanglement breaking. For all these P's in between, instead of positive maps, it's P positive maps which are. And then there's this last one, which is maybe not so well known. Let's just do the case P equals 1 first. So when P equals 1, that's classic entanglement breaking. And this L infinity sub K, you can just think of that as the diagonal K by K matrices. And it says that a map is entanglement breaking if and only if it factors through, I like to think of this as classical, right? Because we have diagonal matrices, everything's commuting. So entanglement breaking maps are the ones that factor through classical. P entanglement breaking, you don't factor through quite classical, but you factor through. This is really a symbol for the block diagonal matrices, which are P by P matrices down the diagonal and 0 every place else.
Wouldn't it be more natural to have just a direct sum of
direct sum
matrices of rank less than P or something like that?
I want to put it this way because, see, this is an abelian C-star algebra in the complex case.
Hybrid information doesn't mean that you can trace out the complex part, the quantum part. It's a tensor product only if you can forget the quantum system in the sensible way. But you don't have to assume that.
So I just like to think of it, it tells us that we factor through classical.
Yeah, sure.
And it's the same in the real or the complex theory, which is the point. So nothing changes there, except we do have this C set, and so it's natural to wonder what's that all about. And so if you're this should be the definition of P-sep entanglement breaking of some sort, right? When you tensor up, you don't become separable, but you become C-separable after you apply. And that's the same as if you complexify over the complex numbers, your P entanglement breaking.
Sorry,
That's-
just another stupid question. What is exactly does CP mean here? I mean, you have a map on the real tensor product of the matrix algebras,
Right.
and then you tensor with the identity on that.
Right.
But it's very different from the real matrices over the real Hilbert space tensor product.
Well, so you're really doing your tensor producting with with Rn,
Yes.
and then you're looking at the matrices that are positive on
So you, yeah, okay.
Rn tensor Rd. So it's just the same definition when you think of it as block matrices. That's when you apply phi to a block matrix and think of that as an NK by NK matrix. And up to level P, when you say that you're P positive, it means up to level P positivity is preserved. But when you tensor with larger dimensional, it might not preserve positivity anymore. And so this sort of entanglement breaking, where you don't entanglement break all the way down to the separable, but just to this C separable. So again, think P is one, so you don't have to deal with all the generalizations. It's the same as the Choi matrix being C separable. So it's separable as a complex matrix, but not separable as a real matrix, even though it is a matrix of real numbers. And again, that corresponds to Choi-Krauss representation with things of rank at most P, except you have to use complex matrices in your Choi-Krauss, even though everything when you're done will add up to real matrices. So it's somehow the complex has to be chosen to all cancel. And now here's the thing that's different. In complex analysis, we're used to the Gelfand-Naimark theorem, which tells us that every time we have an abelian complex C-star algebra, it's continuous functions on a set of points. But abelian real C-star algebras don't have to be functions on a set of points. So it doesn't have to look like an L infinity. It can be something crazy. And that's what happens here is you do factor through classical, but classical doesn't mean functions anymore. Classical just means an abelian real C-star algebra. And so that's what the C-sep does. It exactly captures this fact that real abelian C-star algebras don't have to be algebras of functions. They can be strange. And so all I mean here by real is it's just you're inside a complex C-star algebra and you're a real vector space and closed under products. So that brings me to the last piece. I want to talk about the PPT squared conjecture and what it looks like in the real case. So just to recall, a map is called PPT, or positive partial transpose. The map is completely positive, and when you compose it with transpose, it stays completely positive. The PPT squared conjecture is that if you have a map from D by D complex matrices back to itself, which is PPT, and when you compose it with itself, it's entanglement breaking. In some ways, this is a bad conjecture because PPT states were thought to be useful in quantum repeaters, but because of the PPT squared conjecture, if every time you compose something it becomes entanglement breaking, then you would lose all quantum advantage if you tried to use PPT states in quantum. So it's a conjecture that PPT states are worthless in quantum repeaters. And here's what we know about the conjecture. It's still open. It's true for D equals 2 and 3, and Alexander Mueller here has done a lot of work on these for many families of math. Talk to Alexander if you want to know more of these special classes and things. It doesn't matter if you compose a map with itself or if you compose any two PPT, as long as they're sizes to be compatible for composing. It's equivalent to two when you compose them become entanglement breaking. And then there's some partial positive results. Let me skip this first one for the moment. It's something that was useful in the proof of the next part, which is that if you have a PPT, we can't prove that composed with itself it's entanglement breaking, but we can prove that asymptotically, as you compose it over and over and over, the distance to the entanglement breaking maps goes to 0. So this is like an asymptotic version. And then with Misa and Sam Jacques, we proved that if you're PPT in sort of the analog of doubly stochastic, you're unital and trace preserving, then you only have to compose finitely many times and it becomes entanglement breaking. So there's some K, but it's the proof doesn't allow us to deduce even for a fixed D that there's a fixed K. It's individual to each map, and we have no bounds if you fix D on how large this K might have to be.
You don't have a bound, or do you know that there is
at all? But for each individual map, we can prove there is an individual K. But if K is very, very large, this could be irrelevant, right? If K is 10 billion, then you don't care if you want to use it for building quantum repeaters, because you're not going to need to repeat 10 billion times. But still, it's kind of the best result.
Sorry, you said for each individual phi means you consider all different channels?
No, if you fix phi, so phi goes between some MD to some MD, then there'll be some K, so that when you compose that phi with itself K times, it becomes entanglement breaking.
So it all depends on the dimension.
No, it depends on the phi. We don't have a single K that works for all phi's in dimension D. Just for each individual phi, there is a K.
Is it easier for mixed unitary in the doubly stochastic category? Like if Birkhoff holds, like.
Because those are factorizable.
No, I meant just for the last statement here. If that doesn't help. Okay.
Our proof, it wouldn't help in our proof, no.
What happens if you just use unitality without trace preserving? Can you say anything?
So not on this result, but on this result, it doesn't matter if it's either unital or trace preserving, but both families of maps asymptotically go to the entanglement breaking maps. This one, we need both. We don't, so there is no finite K known if you just have trace preserving or if you just have unital. It's only in the case where you're doubly stochastic, you're unital and trace preserving, that we know there's a K. Now, this one was a step in proving this. If you so for the C-star algebraists in the crowd, there's if you have idempotent PPT maps, and I think this is an interesting family to look at, where phi composed with phi is just phi again. If you're PPT and idempotent, then the range of the map is itself an abelian C-star algebra. So that the range is living inside some D by D matrix algebra, and it isn't an abelian algebra in its original multiplication, but there's this strange multiplication you can put on it that makes it an abelian C-star algebra. So that's what's known in the complex case. And what can we say in the real case? Well, the direct real analog, PPT, is a false conjecture over the real numbers. And here's an example, very simple example. If you look at the map on the 2x2 real matrices given by this Choi matrix, this tells us E11 goes to the identity, E12 goes to that, E21 goes to minus that, E22 goes to the identity, then that map is PPT, but it also happens to be idempotent. If you compose it with itself, you get it back again, but it's not real entanglement breaking. So that shows the direct analog of PPT conjecture is false over the reals. However, if you complexify, when you compose it with itself, it's C entanglement breaking over the complex numbers. So to get the Choi matrix separable, you have to go to complex numbers. In fact, if you think back to the first example, that's exactly the matrix I wrote down on the second slide that I called X. We showed was in C sep, but not separable. So what is a reasonable real version that might help us with the original PPT conjecture? This is something we call the ITP squared conjecture. And so we'll call a map on the reals ITP if it's completely positive. And not only does it stay positive when you compose with transpose, but it's fixed when you compose with transpose. And the reason for this, if you remember back earlier, that if you have something which is separable in the real case, then it's fixed under partial transpose. So this is just saying that PPT, you can think of it as you've got a Choi matrix which is positive, and you do the partial transpose of the Choi matrix and it stays positive. This is asking that when you do the partial transpose of the same Choi matrix, it stays the same. And so that's kind of more natural, I think, in the real case because of this fact that separable matrices are fixed under partial transpose in the real case. And so the conjecture is if you're in the real case, you have a map on real matrices that's ITP, then phi composed with itself is real entanglement breaking. And so what can we say about this conjecture? Well, things we know. First off, we can prove if the complex PPT squared was true, then this one is true. So this is kind of an easier conjecture to work on, maybe. On the other hand, if you prove this one is false, then we know the complex one is false. We don't know if they're equivalent, though. We haven't been able to prove that. We have the analog of the first one of the first theorems, that if it's unital and idempotent, then if you take the range and you do this weird product on the range, it's isomorphic to L infinity K for some K. So it's a real C-star algebra that you can view as functions on something. And in particular, phi composed with phi is entanglement breaking. So if you're ITP, then and either unital or trace preserving, then you asymptotically become real entanglement breaking. So that's the analog of that theorem. And if you're both unital and trace preserving and ITP, then there'll be some power. So if you compose it that many times, you become real entanglement breaking. So it's got all the right analogs of the theorems we do know in the about PPT maps. So let me just finish with some things I would like to know the answer to, but I don't. And I can't prove that if you have a state that's C-separable, separable as a complex state, but not separable as a real state, if it can ever yield a quantum advantage, and if you're doing quantum theory over the reals. It's certainly the case that if you try to use it for, say, these conditional probability densities we're looking at, that you'll just get the local densities out of it. So it can't give you a quantum advantage that way. All the densities it would give you by all the PABs given XYs would just be local probability densities. But I can't rule out that there isn't some other thing in which you could get an advantage from a separable state. The other thing I've thought about a lot in the past was this Hayden Van Dam embezzlement. I won't have enough time to explain what that is here, but I know a few of you know about it. And you can show that in the real case, the same tricks work. And that you can convince someone that you're starting with separable and producing entangled by local operations, which you shouldn't be able to do. That's the idea behind their embezzlements. It's that within all small measurements, it looks entangled, but you know you haven't done this.
But the proof doesn't translate exactly, right? There are some modifications you have to do.
For the real case?
Yeah.
No, you can do the exact, there's one proof of Hayden Van Dam that you can do the exact same proof of. It works real or complex. Not the original Hayden Van Dam, but if you know, well, the proof that's in the paper with Richard Cleve of how to do embezzlements, that works perfectly well, real or complex. The other thing we talk about in there is, can you do exact embezzlement? And we show, even if you allow infinite dimensional Hilbert spaces, you can't do it. You can't exactly produce an entangled state from in this with these local operations. But if you go to the quantum commuting model, you can produce them exactly. And I don't know if that works in real theory, because it all relied on states on complex C-star algebras, and I don't have enough proofs of all the development of the real C-star algebra theory you need to carry out that proof. I also don't know what happens with these C-separable states, right? They're sort of phantom separable. I don't know if you can exactly embezzle in the tensor theory something that's complex separable. I mean, you know, a state that's separable as a complex state, but not separable as a real state, if you can somehow produce it. And the other thing that might make this theory useful is if you have an actual quantum channel, is there some way you can guarantee that the noise is real? Because if you can somehow put a filter or something in so that you get real noise within your quantum system, then you really could look at doing everything over the real Hilbert spaces and studying real channels, in which case, you know, you might be able to build a quantum repeater that works if you can filter out the complex part of the noise, because we've seen that in the real case, you can have PPT things that's never become entanglement breaking over the real case. So these are things that I think are possible thought troubles that might make the real worthwhile. That's all I had to say today.